Hey everyone, welcome to today's Explainer. If you're a grade 8 student looking to totally master some essential geometry concepts, well, you're in exactly the right place. Today, we're basically putting on our detective hats. Your specific learning target is this. You are going to learn how to identify congruent figures, explain how their corresponding sides and angles match perfectly, and use rigid transformations or precise measurements as concrete evidence. We aren't just guessing here, we're going to learn how to prove our answers mathematically.
Okay, let's just dive right in. To solve cases in geometry, we need to know exactly what we're looking for, right? Our baseline standard today is the word congruent. By definition, two figures are congruent if one can be obtained from the other by a sequence of rotations, reflections, and translations. In simpler terms, it just means two shapes are absolutely 100% identical in size and shape, even if they're scattered in totally different places on a coordinate plane. Now, when we compare two congruent figures, we've got to look at their specific parts. First up, we have corresponding sides. These are the sides in the same relative position on two different polygons that have the exact same length. If you imagine, say, picking up one shape and laying it directly on top of the other, the corresponding sides are those boundary lines that match up perfectly, edge to edge with literally zero overhang. But it's not just the outer boundaries that matter here. We also have corresponding angles. These are the angles in the same relative position on two different polygons that have the exact same measure. Just like the sides, the corners, or angles of congruent shapes must also map onto one another flawlessly. If one angle is 90 degrees, its corresponding angle on the congruent shape must be exactly 90 degrees for sure. So how do we actually prove that two shapes can map onto each other perfectly like that? We use our geometric detective tools. Tool number 1 is a translation. This is a movement that slides a figure along a straight line without turning or flipping it. Think of it like a simple straight slide across the coordinate plane, maybe moving a few units up and a few units over to the right. The shape itself doesn't change at all, just its location. Let's keep that energy high, because tool number 2 is honestly just as important. This is a rotation. A rotation is a movement that turns a figure around a fixed center point. Imagine turning a steering wheel on a car or the hand sweeping around a clock. You can rotate a shape 90 degrees, 180 degrees, or really any amount. But the size and the internal shape, they remain perfectly intact. And then we have our third detective tool, which is a reflection. A reflection is a movement that flips a figure across a line, creating a mirror image. It's exactly like looking in a mirror. If you have a triangle on the left side of the y-axis, a reflection flips it right over that axis to the other side. It faces the opposite direction, but all the distances and angles stay exactly the same. So here is the absolutely crucial point. All three of these tools, translations, rotations, and reflections, fall under a master category called a rigid transformation. A rigid transformation is a sequence that strictly preserves distance and angle measures. They never, ever stretch or shrink the shape. Because they keep everything rigid and unchanged, they are the ultimate proof that two figures are congruent. Let's actually put this into practice and look at a real case. Here are our suspects for this investigation. On the left, we have triangle ABC with specific side lengths of 3, 4, and 5. On the right, scattered elsewhere on the coordinate plane, we have triangle DEF. I want you to think about these two shapes for a second. Do you think these two scattered shapes are actually congruent? Well, let's use our tools to find out. Let's see how this builds into concrete proof. Step 1. We select our first suspect, triangle ABC. Step 2. We perform a rigid translation, sliding it exactly 4 units right and 2 units up along the coordinate plane. Step 3. We observe. As it lands on top of triangle DEF, we see that the length and angle measures are completely preserved. It maps perfectly. This rigid translation is our mathematical proof that they are indeed congruent. And this brilliantly illustrates how we can identify the specific named corresponding parts once they map onto each other. Let's trace it out. Side AB on the first triangle matches side DE on the second perfectly. Side BC matches side EF. Looking at the corners, angle A maps directly onto angle D, and angle B maps directly onto angle E. Every single part has a corresponding identical partner. Now I want to talk about a massive trap you really need to avoid. Let's be honest, our hand-drawn math sketches are usually kind of terrible anyway, right? Just because a quick sketch looks like it's congruent does not mean it actually is. Visual guessing just isn't good enough in geometry. As detectives, we always require proof. You must either provide precise measurements of the sides and angles, or you must show a sequence of rigid transformations that map one figure to the other. All right, it's time to put you in the hot seat for a quick learning check. Here is the question. If you stretch a shape to make it fit over another, have you proven they are congruent? I want you to pause this explainer right now, think about our definitions, and answer out loud. Go ahead, pause it for a sec. Welcome back. Okay, if you answered no, you completely nailed it. Absolutely not. Stretching fundamentally changes the side lengths of a figure. Because the distance is altered, it completely breaks the rules of a rigid transformation. Without rigid transformations preserving the exact sizes, you destroy any chance of congruence. Great job if you caught that.
Let's hit you with a second check, just to make absolutely sure you've mastered this. Question 2. If triangle GHI is a reflection of triangle JKL, do their corresponding angles have the same measure? Once again, hit that pause button, figure it out using what we've learned, and then press play when you're ready. All right, let's see how you did. The answer is yes. Remember, a reflection is simply a mirror image. It's one of our 3 core rigid transformations. And the golden rule of rigid transformations is that they strictly preserve distance and angle measures, so the angles will be perfectly identical. You've done fantastic work today. To really lock this in, let's recap our 3 most important takeaways. First, congruent figures have exact matching corresponding sides and corresponding angles. Second, we prove congruence using rigid transformations like translations, rotations, and reflections. Third, a visual sketch is never enough proof. You must use precise measurements or transformations. To end today's explainer on a high note, I want to leave you with a final provocative thought to take with you to your next math class. If you rotate a square 90 degrees on a coordinate plane, how do you prove the new square is congruent to the original? Think about what specific properties are preserved during that rotation to formulate your answer. Keep investigating, keep questioning, and I'll catch you in the next explainer.